Everyone, welcome back. Here's one more example about related rates. It's an example that requires recall of something from long ago. It may have been 3 or 4 years ago for you, depending on when you'd learned something called related triangles. So remember your T pattern, your Z pattern, all those things, F pattern, remember those? You remember, well, not all of that is coming back. We just need one thing from that era. We need similar triangles. So this question says we have a water tank that has the shape of a cone. This cone has a big height, capital H of 10, and a top radius, capital R of 5, and those are labeled in the picture. At this instant, the water line is little h equals 3. So I'm going to label that because it isn't currently labeled. So that's little h. Little h is equal to 3. And the tank is being filled at a rate of 2 cubic meters per second. So that's another piece of information. I'm going to call that V prime because it's a rate of change of the volume is 2. What is the rate of change of the water line's height at this time? So what we want is h prime. We're told that h is 10 and r is 5. So before launching into math, let's picture what's happening here. Water is being poured into the tank from up here, being poured in, and this water level is going up and going up and going up. Water level keeps rising as water is being added. As the water level goes up, so as h increases, notice that the radius, this little small radius here, it keeps increasing as well. Notice what does not change as you add water. The big H, the height of the entire container, and the big R, the radius of the entire container, does not change as you add water, at least to a first approximation. There is going to be some stretching, but it's negligible. So I'm going to label this little radius here, I'll label it little r, because we might need that. Now keep in mind, we are interested in the blue shaded region. We're interested in that rate of change of the height of that much. The other stuff, the container, that's information we'll have to take into consideration in some other way. So I'm going to go back to the model that we're told, the volume of a cone with radius little r and height little h. V is 1/3 pi r squared h. And think about what we would do if we wanted to find v prime, or we have v prime, if we wanted to find h prime. We need to know something about r, which, like little r, we don't know what little r is. And little h, we know little h is equal to 3, but when we take the derivative, we're going to have a little h prime, we're going to have a little r prime, and we're going to have little r. Like, we're missing a lot of information. So we don't have r, we don't have little r, we don't have little r prime, and we want h prime. So it's like we have 3 unknowns. So what are we going to do? I'll show you. I'm going to draw a triangle. And I draw a little triangle inside there. And I'll start labeling the sides. So this side is H. This big side is capital H. This big side there is R, capital R. And this side going left and right is little r. Just labeling those pieces. Now I'm going to do something that you're not going to like. I'm going to put a theta there. Yeah, a little bit of trig, and then I'm going to erase it. So everything I'm going to write in green, I'll erase after. just want to convince you that what I'm about to show you has a basis in trigonometry. Tan theta. Do you remember what tan of theta is in terms of SOHCAHTOA? Tan is the TOA, opposite over adjacent. So the opposite is big R divided by big H. But that's the big triangle. Let's also look at the little triangle. It's also equal to little r over little h. Maybe I won't erase it. Maybe I'll leave it. We don't need it. We just need this. This is similar triangles. That's kind of a proof of it. Your opposite over your adjacent, you can either use the big triangle or little triangle. They both have to be equal to tan, like tan theta has to be equal to both ratios. It's the same tan theta for each. That means that the ratios have to be equal to each other. Big R over big H is equal to little r over little h. We can rearrange. We can get little r in terms of h. So then little r is equal to h times big R over big H. And these things are constant. So even though we haven't taken the derivative yet, the fact that they're constant means that we can plug them in right now. We don't have to like have them haunt us all the way through the calculation. So that's h times 10 over 5. So that's equal to 2h. Now we can plug that into the volume formula. So our volume is 1/3 times pi. R is 2h. So V is 1/3 pi. 2h squared is 4h squared times h. So we got 4 squared times h. And I put all the constants up front. So 4/3 pi h cubed. Maybe reminds you of something. Not that it matters. Right now, we want h prime. We're going to take the derivative. Oh, I don't have any more space, so I've got to cram it all in. So we'll take the derivative. We get v prime is equal to 4 pi h squared h prime. What happened to the 3? The 3 came down and canceled. The 3 was already in the denominator. So then this means that h prime, the thing that we're after, is equal to v prime divided by 4 pi h squared. Then we can plug in our data. V prime is 2. We have 4 pi times h squared. H is 3, so times 3 squared. And we have our answer. So 2 over 4 partially cancels. We've got 2 in the denominator. So 1 over 18 pi would be our final answer. So that's the rate of change of the water level's height. A very nasty question. And it's a preview of a standard problem in Calculus 1000, which I know some of you are taking, and it's much more challenging than Math 0110. That's it for related rates. Take care.